In this video, we're going to be finding the area between two curves. So our directions are going to be either to find the area enclosed or the area between two functions, and then we're also going to be looking at some applications that relate to area. So let's look at what we know already about area. We know that if we want to find the area trapped between our function f of x and the x-axis, so this blue region in here, if we want to find that area, all I need to do is take the integral from a to b of f of x dx. Now we also know that if the function goes below the x-axis, then our area looks a little different. So we think of this area here that's above the x-axis as the positive area. Let's call this a sub 1. And we think of this area here that's below the x-axis, this is a negative area, and we call this a sub 2. So our definite integral from a to b of f of x dx equals a sub 1 minus a sub 2. So we have a new problem. Now, instead of just finding the area trapped between f of x and g of x, we want to find the area between a function f of x and g of x. So we want to find this area in here. So we know from what we just looked at that if we want to find the area between f of x and the x-axis, that gives us this big area here. But the problem is that this includes some extra area. It includes this green area in here, and this is extra that we don't want if we want the area between our f of x and our g of x. So the area between f of x and the x-axis that includes that extra is this integral. And we actually know the area of the green region. The green region has area, we go from a to b, but our function that's we're looking at between the x-axis and our function, this time it's g of x. So if we're trying to find just the area of that blue region, what we've got to do is we've got to take the red shaded region and subtract off the green shaded region. So the area of our blue region is just our area of f of x dx minus the area of g of x dx, and if we want to combine that into one integral, we go from a to b of f of x minus g of x dx. So let's look at the general formula. So to find the area between two curves, what you do is you take the definite integral of your top curve minus your bottom curve. So if we look at our region again, so it looked kind of like this. And this function here was our g of x, and this function here was our f of x. The f of x, this defines the top side of our region. So this is the top of our curve. And this side here, this is the bottom of our curve. So we're going to take top minus bottom. And then we also have to have these limits on our integral correct. And it's always the left side of your region. So this was A, and the right side of your region, that was B. So we're going to go from A to B of top minus bottom. So one interesting question is, what do we do if the region that we're looking for doesn't reside completely above that x-axis? So when we were doing the integral from a to b, if we were trying to find this area here, it's not completely obvious that this part in here would count correctly, because we would usually think of this as say negative. So what we do in order to figure out how to deal with this is think about, okay, well, if we scoot these functions up the same amount by adding some value m to both functions, then you're going to have the same shape, but it's going to be scooted up into the first quadrant. And now we don't have any problems with things counting as negative area. So let's find the area of this region over here. This would be a to b. We're going to have f of x plus m, and then minus g of x plus m dx. And if you look here, when you combine like terms and distribute this negative sign here, we have a plus m and a minus m, and they cancel each other out. So we just end up with the integral from a to b of f of x minus g of x dx. So it's the top curve minus the bottom curve. So it doesn't matter if it falls below that x-axis, because we can just scoot both functions up. And so we don't even bother scooting them up. We can just take top function minus bottom function. So let's look at an example. And before we actually start our example, let's look at the general steps for solving an area between two curves problem. When you're trying to find the area of a region, it always helps to be able to visualize, to see the region that you're trying to find the area of. So once you find you've got them graphed, that's the first step. Then you're going to determine which curve is the top curve and which curve is the bottom curve. Then you're going to identify the lower and upper x values so that you can have the limits on your definite integral. You're going to write your definite integral, and then you're going to evaluate it. So let's look at this problem where we're supposed to find the area enclosed by y equals x squared and y equals x plus 2. So I'm going to grab my calculator over here, and I am going to put my function y equals x squared in my y1, and in y2 I'm going to have y equals x plus 2. And I'm going to go ahead and just zoom to one of my standard windows. Let's zoom decimal. Let's see if that works. Okay, so that looks pretty good, but if you can see, I think part of my region is cut off here, so let me change my upper y's. So let's change my y max to be, say, 6. Okay, so now I see my region, and so if I were to graph what I'm trying to find the area of, I'm looking at this type of shape. So I've got my parabola, and then I've got my line. Sorry, this is kind of sloppy, but the region that I'm trying to find the area of is this region in here. So this is the area that's enclosed, and the reason why we use this word enclosed is because all sides of our shape are bounded by our curves, so that the curves make all sides of the shape. So now we're ready to determine which is the top curve and which is the bottom curve. This curve right here, this is the top, and it's actually a line. And this right here, this is the bottom. Okay, this side here makes the top because it creates the top side of our shape, and this here is the bottom because it creates the bottom side of our shape. So now we're ready to find or to start building that definite integral and to figure out what our lower and upper limits are. So we need to figure out what is the value here and what is the value here. I need to figure out what x values our region goes between. So I've got my y values, my top and my bottom, and these are my x values, my left and my right side. So I can use my calculator to do that, or I could solve it algebraically. Let's go ahead and try using our calculator. What I want to do is I want to find where these two curves intersect. So I can go second trace, I can choose 5, and then it asks me for first curve. I just press enter. It asks me for a second curve. I press enter, and it says guess. So we need to move over near the intersection that I want to find. So I'm going to move over here. Do you see my little spider moving along the graph? So I want to be about right there, and then I'm going to press enter, and it tells me x equals -1. So this value here is at x equals -1. I don't care what the y is, I only care about the x's. So let's find this second one. The second one, we get x equals 2. And so now we're ready to write and evaluate our definite integral. We're going to go from -1 up to 2. Our top curve is the line. It's x plus 2. And then we're going to subtract off our bottom curve. That's x squared dx. We're going to do our antiderivative. We're going to have x squared over 2 plus 2x minus x cubed over 3. We're going to go from -1 up to 2. And so when I plug in 2, I'm going to have 2 squared is 4 divided by 2 plus 2 times 2, that's 4, minus 2 cubed, that's 8 over 3. And then subtract off -1 squared is 1/2 minus 2 minus -1/3. When I combine like terms, and you can see we get 10/3 minus a -7/6, which is 9/2. In the second problem, we're doing a very similar problem, but we're trying to find the area enclosed between y equals x cubed and y equals x. So once again, let's graph this region. So you can see I have my two functions in here. I'm going to zoom decimal again. This time, this window is a little bit too small. Most of my area is right in this region, so I'm going to change my window again, and instead of going from -4.7 to 4.7, I'm just going to go from -2 to 2, and then -2 to 2 on the x's also. Whoops. And then -2 to 2 on the y's also. This blew our picture up a bit for us, and we can see a little bit better. When you look at this, hopefully you notice that we have two regions, this region over here and this region over here. And the other thing you should notice is that the top function changes between the two. So over here, in this region over here, the top function is x cubed and the bottom function is x. But over here, the top function is x and the bottom function is x cubed. The second thing I want you to notice is that these shapes, there's a lot of symmetry going on, and in fact they're the exact same shape, it's just flipped over. And so we don't actually need to find the area of both shapes, we can just find the area of one of them and then multiply by 2. So I want you to pause the video and see if you can find the area of one of these shapes, multiply by 2 so that you can find the area enclosed by these two functions. Did you give it a try? Here is what your answer should be. So we take the integral 2 times the integral from 0 to 1 of x minus x cubed dx. You could have also done the integral of 2 times -1 to 0 of, this time it would be x cubed minus x. We would have gotten the same answer using this other method. Do the definite integral, plug in the top and upper and lower limits, subtract, and you should get 1/2. In this next example, we change the wording a little bit. It says find the area between y equals -x and y equals e to the -x and y equals -x for x in the interval 0 to 1. So remember, the first step is always to graph. So let's graph. I've got my two functions in my y equals. Let's use one of our preset windows. Let's once again zoom decimal. And you'll notice that this time there isn't a region that is enclosed. It's not making, it doesn't intersect and make all sides of a shape. So what we're looking at is the specifically for x in 0, 1. So let's change our window a bit. Let's go from, say, -1 up to 2. And we're looking at x between 0 and 1. So if we drew that shape over here, here's my e to the negative x function, and here's my y equals negative x function. Here's 1, and so if I'm looking at between 0 and 1, I've got, here is one side of my shape, and here is the other side of my shape. This is my left and right sides, and then this is my top curve, and this is my bottom curve. So this x equals 0 and x equals 1, they give us the left and right sides of our region. So we're going to do the same problem the same way that we did when it was enclosed. We're going to take the integral. We're going to go from 0 to 1. We're going to have the top curve. The top curve is e to the negative x minus the bottom curve, so minus negative x dx. So we're looking at the integral from 0 to 1 of e to the negative x plus x dx. So go ahead and pause the video and do this integral and then start it back up. So here's my completed work. I did the antiderivative. One little thing to note here is that since our exponent here is negative x, not just plain x, you'd either need to do substitution or know how it works. So it's going to be e to the negative x, but you have to divide out or multiply by the derivative of the inside. So that's where this negative comes from. And here we have x squared over 2 from 0 to 1. The other little sticking point is oftentimes when we plug in 0, we end up with 0. But if you notice here, we have negative e to the 0, and e to the 0 equals 1. So that thing just equals 1. So you have to watch out for that. This last problem is an application, and this time they tell us, suppose that our monthly revenue for selling MP3 players is given by R of t equals 500t plus $10,000 per month, where t represents the number of months since the start of the year. We're also told that the monthly costs are C of t, which equals 200t plus $2,000 per month, and we're supposed to find the area between the graphs R of t and C of t for t between 6 and 12 and interpret this answer. So once again, just like usual, we're going to first graph our two functions. I've got my R of t in y1 and my C of t in y2. Our window, we want to go from 6 to 12. I'm going to go from 0 up to 12, and then we'll narrow in on 6 to 12. And let's make an x scale of 2, and then let's zoom fit, and we might need to adjust that a bit. And we do. Let's look at our window again. I'm going to go from 0 instead of 2,000 up to 16,000 and make the y scale be 1,000. So if I look at that graph, what I've got going on here, here's my revenue function, here's my cost function, and I'm looking at 6 to 12, so I need to find this region in here. So let's find that region first. So our integral is going to be from 6 to 12. Our revenue function is the top function, and our cost function is the bottom function. Now hopefully you're thinking revenue minus cost, that probably is profit, because we're used to seeing R minus C. And so when you plug our two actual functions in, we're going to have 500t plus 10,000 minus, be careful to distribute that negative sign, so we're taking the definite integral of 6 to 12 of 300t minus or plus 8,000 dt. So I'm going to let you complete the actual definite integral here on your own and then restart the video. So I've completed my definite integral. Let's figure out what the units are in this value. So I end up with 64,200, and what we're looking at is dollars. And what happened to the per month? Well, when we're taking the integral, we end up losing this per month because we're finding the total change in value of our R of t minus C of t. And if we're going from 6 to 12, this is going to be that profit in the second half of the year. So that's it for this video. Hope it's helpful.